So this is lecture 3.1 of the foundations of machine learning, learning with infinite hypothesis sets. This is one of the greatest lectures ever, and we're going to have a lot of fun learning about, how you learn with infinite hypothesis sets. So the motivation is with an infinite hypothesis set edge, the error bounds of the previous lectures are not informative because all of them used the cardinality of the set. So when there is an infinite number of them, they're not really informative. Is efficient learning from a finite sample even possible when the h is infinite? It is possible because if you remember the one we did with the axis aligned rectangles, it was possible. But any other, like, because we leveraged geometry in that sense, it was possible. But is there any other way? Can we reduce the infinite case to a finite set and project over finite samples, whatever? Are there useful measures of complexity for infinite hypothesis sets? This is what we're going to study now. Basically the question is infinite number of functions but a finite sample, how do we even learn? So the first topic of this lecture is Rademacher complexity, and this is a way to quantify how complex our set of functions is. So let capital G be a family of functions mapping from set Z to A to B. Alright, some interval A to B. Sample S be m number of samples in this capital set Z. Alright. Sigma i's are Rademacher variables. What does this mean? This means there are independent, uniform random variables taking value in -1 and +1. So they are like +1, -1, that's it. And they are randomly sampled. And they take +1, -1 with equal probability, whatever. So the empirical Rademacher complexity is the script R with a hat, and it's empirical because it is calculated on this sample S, a particular sample S, and it is a function which takes the input the entire family of functions. What is this? Is an expectation over all of these Rademacher variables, the supremum over all functions, and this number. Alright, what is this number? This number, if Rademacher variables are just +1, -1, like sigma 1 is either +1 or sigma 1 is either -1, etc., etc., all of these m, and g is a function which takes a value between a and b. What this is a dot product of this random noise with our function output, and now we are taking a supremum over all functions g and an average. The average is fine, whatever. The supremum over all g, what this means is that this particular quantity is trying to measure that in our capital G set, capital G, the entire family of function, is there a function which absolutely can correlate to any random noise present ever? Like, there could be one scenario where all of these are ones, all sigmas are ones. In that case, is there a function which is b at all times? G of z1 is b, g of z2 is b, g of z3 is b, all of them are b. In that case, this particular number will be really high. Sigma 1s are 1 and g of zi is the max possible that it can be. So this dot product is really high. There could be one scenario where all of them are -1, in which case g of zi is the minimum that it can be, which is small a, and then it could be like, it is, again, this is the supremum that we are calculating. There would be one case where all of them are 1, all of these sigmas are 1 except let's say sigma m was -1. In that case, we want g of z1 to be b, g of z2 to be g of z3 to be b, blah blah blah, and g of zm to be a. So such a function, does it even exist? If it exists, then it has a high, this supremum is really high, and therefore this complexity is really high. What it means is, am I able to find a function which is able to correlate with any sort of random noise? Basically, this variable, this Rademacher complexity, is trying to evaluate that if I was allowed to overfit as much as possible, can I even do that? Can I even overfit to the max possible capabilities of the, for example, let's say capital G was neural networks of 2 layers with 10 neurons per layer. Can I overfit this to as many samples as I can? Let's say 10 samples. How much can I overfit? If I can overfit to 10 random plus minus 1 signs, that means that this function has a quite a high amount of, representative power. Instead, if I cannot even overfit, like, that's the question that we are trying to see. Can it even overfit? I don't really care how good of a generalization this is, but if I was allowed to learn any random possible noise, would I be able to? That is what this is learning, and this comes because of the supremum. So what we are doing is trying to evaluate this correlation of every possible g in that capital set. So the one which gives the highest possible correlation, that is what we are counting for a particular sigma. Like, that's what the expectation is counting, the best possible g which correlates with random noise. Obviously, finding this is, again, it's an infinite class. That's the entire premise. But yet, this is what we're trying to accomplish, and this makes sense. If I am given if I'm given a class of functions, am I able to, how good of a fit can I fit to random noise? So you gave me m plus 1 minus 1 plus 1 minus 1. I look through all of my roster and see which function gives the best possible fit, and I send that to the expectation, and I keep doing it again and again and again. So if I'm able to find a good particular fit for every possible of these m2 to the m combinations, my class G would have a high complexity. If instead this was just a constant number, let's say there was just a 1 in my entire G is infinite, but all of these values are just 1. In that case, what would happen is this expectation, because it's over the random variable sigma, they could be plus 1, minus 1, whatever, this will turn out to be 0. And it makes sense because there is no representational complexity in our class. All it is just a constant number. So it has 0 Rademacher, it has 0 complexity. This is what this Rademacher complexity is trying to measure. How good of a fit can I be with random noise if there is no restriction whatsoever? Right? This is the main key idea of complexity of a family of functions. This is the same thing. It's just written explicitly. Like, this dot product is written explicitly, but this is the same thing. So let G be a family of functions mapping from Z to whatever interval. Then the empirical Rademacher complexity of G is, again, the expectation over Rademacher variables, supremum over the entire family of the correlation between that function and the Rademacher variables. And Rademacher variables are independent uniform random variables taking between -1 and 1, and sample is m's randomly sampled samples, whatever. So that's the empirical Rademacher complexity, because it takes an input, the sample. Now the real Rademacher complexity is the expectation of empirical Rademacher complexity over all possible s's. So if I take the expectation over d to the m, basically take m samples, every possible m sample, and take the Rademacher complexity, empirical Rademacher complexity, and average it, that is the Rademacher complexity of my class G. Fine. This is easy, fine. Rademacher complexity is easy to understand once you understand that empirical Rademacher complexity. Now, let capital G be a family of functions mapping from Z to 0, 1. Now A to B is 0 to 1. And therefore, any delta with probability at least 1 minus delta, the following holds. What is this? This means that the expectation of G on a sample is less than the empirical average of G, plus twice the Rademacher complexity of G, plus some number which comes from, this looks familiar, it comes from the McDermid or Hofting things. Again, or the expectation of G is the empirical, plus twice the empirical Rademacher complexity, plus 3 times some number which comes from Hofting's or whatever. So the proof is, we will apply McDermid's inequality to this quantity, this phi of s. What is phi of s? Phi of s is a function which takes a sample as an input and computes the supremum of this quantity. The supremum is over the entire thing. What is this entire thing? This entire thing is how worse is my empirical error compared to my real error for a particular function G in that set, and what is the worst that it is. That is basically the supremum. So the supremum of expectation of G minus the empirical average of this G, and empirical average is this number and expectation is, well, this number. So basically we have this two quantities here, but we have a supremum. And now we will apply Macdermid's inequality to this. Basically just change one point of S and make it S prime and see how this quantity changes. This is the supremum of the expectation of G minus the empirical of G of this given sample. Fine. So we change it to S prime. We have the supremum of expectation G minus expectation of empirical of S prime minus the supremum of expectation G, which is the same, minus empirical on S, empirical average on S. Now sup A minus sup B is always less than supremum of A minus B. Why? Supremum of A minus supremum of B is always less than supremum of total A minus B. That is just the way the sup function works. Fine. And now when we pull this together, the expectations will cancel amongst one another, and what we have is the supremum of the empirical on S versus the empirical on S prime. Now S and S prime only differ by one variable. Let's say let that be mth. Let's call that mth. Doesn't matter. This becomes, all of them are the same, so all of the rest cancel out. This becomes 1 over m gzm minus gzm prime. Basically the one point which we sampled, the one point which we changed. And because G takes value between 0 and 1, this can only be less than 1, right? And therefore the supremum of 1 over m blah can only be less than 1 over m. So this lends us to application of Macdermid, because now we have concluded that this quantity, when we switch a point to another point, it can only change by 1 over m. So by Macdermid's inequality, with probability at least 1 over delta by 2, phi of S is less than the expectation phi of S plus log 1 over delta by 2 divided by 2m. This is the application of Macdermid's inequality. You can look it up. We observed that these two quantities, the phi of S, which is the supremum of, which is how bad my real error is compared to my empirical error, or how bad is this gap. And if I change one S to S prime, this gap can only and only increase by 1 over m, or only change by 1 over m. So it is tightly concentrated around its mean, and with probability 1 over delta over 2, it is always, it's less than the mean plus some small quantity. Now we want to bound this expectation, because what we have is phi of S is given. Phi of S is supremum of this number, which will always be greater than that actual number, and we can write phi of S, because it is the supremum, it is greater than equal to expectation G minus 1 over m, the empirical expectation of a particular G, because it's a supremum over all G's, right? So if we are able to bound now this, if we are able to bound this expectation from the right hand side, we have something on the left hand side, and which is exactly equal to this, basically, you know what I'm trying to say. We will come back to it again. So now we are left with bounding this quantity, expectation of phi of S, and this will be, I don't know, it relates somewhere to the Rademacher complexity, because that's what we are seeing. So expectation phi of S over S is expectation S supremum over all G. I just wrote the definition. Expectation G minus expectation, empirical expectation S of G, whatever. Now if I were to introduce an expectation S prime, basically sample S prime as well, sample S as well, and take the expectation of the expectation. This quantity does not depend on S prime, so taking this expectation over this does not change. I'm talking about this expectation. This expectation over this particular variable does not impact it. But if I introduce this expectation S prime, I can write the insides as the empirical S prime. So what I take is the empirical expectation over the S prime and take the expectation over the entire S prime. So we come back to this one. That's the linearity of expectation. And by doing that, I can also include this expectation over this, because it does not change. And why am I doing this? I am doing this so that I can pull this expectation S prime outside with an inequality. This is sub-additivity of supremum, or call it Jensen's inequality, because supremum is a convex function. So the Jensen's inequality states that the expectation of the convex function is always greater than the function of the expectation. So now that we have S and S prime outside, we have what we have inside is the supremum over empirical on S prime minus empirical on S. Now things are looking a little bit more easy to deal with. S and S prime only differ by one variable. So this thing, this particular thing is just the difference between the ith, the wait, what? I guess S prime is not something which is just differs by one. I think, okay, so I made a mistake. S prime is a completely new m point data set. Doesn't matter. It doesn't matter to us, because now we have this 1 over m, and gzi minus gzi prime. Sure. Gzi prime minus gzi. Sure. Now what happens is, now what we are trying to do is, you can see that gzi takes value between 0 and 1, right? And gzi prime takes again value between 0 and 1. So this quantity can take values between -1 to 1. Now if I introduce a Rademacher variable sigma I, what happens is when gzi prime minus gzi was, let's say, 1 and sigma I was 1, then this quantity is the same. When sigma I was -1, this becomes negative of that thing. And because we are taking expectation over all possible s's and ss primes, the negative of this is going to happen somewhere else in the expectation, where zi and zi prime were swapped. So essentially, by introducing this Rademacher variables, all we are doing is changing the ordering of our expectation. The overall value does not change. Let's try to convince ourselves that this is indeed the case. When I write this particular line, what I have is, I fix a function g, I take samples s and s prime, and I calculate the empirical difference. Let's call it the empirical difference of a function on these 2 points. Right? I find the best possible there is, and I take the average. Then that's what happens. I pick s and s prime, I take the empirical difference, and I pick the best possible g, which gives me the highest empirical difference. Then I pick another s and s prime, and I do it again. Now let's say I were to introduce a sigma I, which can either be +1 or -1. Let's say sigma I was +1. When sigma I was +1, this doesn't change. This does not change at all, because it's the same as that one. When some sigma I was -1, the empirical difference now will be when sigma I was -1, a particular sigma I was -1, the rest of the other remain the same, but this one has come with a negative sign, and that can happen if s and s prime, this particular z and zi prime were swapped. But because we are taking an expectation over s and s prime over the entirety, this swap mechanism also happens somewhere else with sigma I -1 again. So essentially, I kind of see it happening that this is the same as the upper one. Okay, fine, whatever. Let's accept that for now and move ahead. So what happens is, now that we have supremum of a minus b, it is always going to be less than supremum of a plus supremum of b. We can write that supremum sub-additivity, and split the expectation into two, one which only has s primes and one which has s's, with a negative in sigma I. But because sigma I and minus sigma I are again Rademacher variables, this is again the same thing as this one. Both of these things are exactly the same, because minus sigma I is same as sigma I. Because it's a Rademacher variable, you can just flip the sign and it's the same thing. Because in the end, what is it? It's trying to measure how good of a correlation you can have with random noise, right? So if I flip the random noise by -1, It's still random noise, essentially. So this expectation is the same as this expectation. So this is twice of this, and this is the expectation over samples supremum of this. So this is the real Rademacher complexity, not the empirical Rademacher complexity, because the empirical Rademacher complexity was an expectation over sigma, just the expectation over Rademacher variables. This is an expectation over Rademacher variables and all samples. So this is twice the so what we have concluded is the expectation of phi of s over the samples is less than twice the Rademacher complexity of this G. And the main key idea was this one, I think, of this entire slide. And does this make sense? Does this make sense? I sample, let's fix S and S prime for once. And now we are taking expectation over all sigma i's. If I swap zi and zi prime, essentially I have turned sigma I to minus sigma I. And that happens because we are taking an expectation over sigma I. So basically, this makes sense. I mean, the expectation over all three of these is the same as expectation over this. Okay, fine. Now we have the real Rademacher complexity in terms of the expectation. We also want to see the empirical Rademacher complexity in terms of the expectation of phi of s, and that can be done because changing one point of s makes the empirical Rademacher complexity vary by at most 1 over m. So again, by McDermott's inequality with probability at least 1 minus delta over 2, you can do this. Why is this the case? Why is changing one point of s makes the empirical vary by at most 1 over m? It comes again from this particular thing. By changing one point, the Rademacher complexity, all of the rest remain the same. Only one changes, and it can change by at most 1 because it can take value between 0 and 1 only. So this supremum can change at most by 1 over m. So the empirical Rademacher complexity can change by at most 1 over m. So it's tightly concentrated around its mean, and therefore with 1 over delta over 2, we have that the real Rademacher complexity is less than the empirical Rademacher complexity plus some number. Now by the union bound, we have 1 over delta by 2 this quantity, and we have 1 over delta by 2 this quantity, and we have that the expectation of phi of s is 2 times the real Rademacher complexity, less than at least. So we can multiply this by 2 and add these two together. So we have phi of s is less than twice the empirical Rademacher complexity plus 3 times log 2 over delta over 2m. Combining this inequality and this inequality and this inequality. Okay. So now we had the phi of s is less than twice the empirical Rademacher complexity plus 3 times this, and phi of s was the supremum of it, whatever. So this number is this one is present because phi of s can only be, because it's a supremum, it can only be greater than the expectation of some g minus 1 over m g, the empirical g, and it is less than twice the Rademacher complexity empirical, and it is less than twice the Rademacher complexity, the real Rademacher complexity, which just comes from putting expectation phi of s in this one. And you might notice that this is 1 over delta, not 2 over delta, but because we were dealing with delta over 2 here, we substitute delta as 2 delta in this, and that results in this. Basically, these equations are correct, they hold, they are right. What this means is that, to comment on how far our real risk or real quantity could be far from its empirical, you need the Rademacher complexity of that particular class or its empirical Rademacher complexity. Now we will look at loss functions. So suppose H be a family of functions taking value in +1 -1, let's say some sort of a classifier, and G be a family of 0 1 loss functions. So what G is, take x and y, and when h of x is not equal to y, you make it 1, otherwise you make it 0. So now the Rademacher complexity of G is half the Rademacher complexity of H. Let's not even look at the proof. Let's see why this is true for once. Like, I have intuition on this. H is a family of functions, right? It can have 4 distinct values in the truth table. Both are +1, both are -1. One is -1 and +1, one is +1 and -1. There are 4 distinct quantitative numbers that it can be. What this loss function does is, when they are same, gives it 0. When they're different, makes it 1. So when there are 1 and 1, it is 0. When there are -1 and -1, it is 0. When they are +1 -1, it is 1. When there are -1 +1, it is 1. So it reduced the expressive power of 4 distinct ones to just 2. Where H was able to distinguish between 4 cases, G, which is a loss function composed on this, can only distinguish between 2. So it is pretty clear, like it seems pretty intuitive, that the complexity by composing the loss function has become half. And let's see why that happens. I mean, we can have a look at it by proof. Rademacher complexity of this G, which is the loss function, is expectation over samples and Rademacher variables, supremum of H, supremum over H, and take the best, sigma I 1, and when h of xi is not equal to yi, it becomes 1, otherwise it's 0. That's the function G. That is the definition of G, right? So now you can write this as 1/2 1 minus yi h of xi. So when yi is equal to h of xi, the multiplication, that product is 1. Either it's 1 and 1, so it's 1, or it's -1 and 1, -1 and -1, so it's again 1. So 1 minus 1 is 0, so this number is 0. But when they are different, the product is -1, so this becomes 1 with the half. So this is exactly the same as the one written up above. Now we can split this into 2. The first is just half supremum of sigma I, and it does not depend on the this quantity. This first half does not depend on the hypothesis sets whatsoever. It just depends on the Rademacher complexity, and Rademacher complexity in expectation is 0 because it's a -1 and +1 variable. This one, on the other hand, we can take the half outside, and it's a supremum over all h 1 over m, and this is just the Rademacher complexity of our function h of xi. Why? Because yi times sigma I is again another Rademacher variable with a -2. That doesn't matter. I can absorb the minus in sigma I. It's again random noise, and I can multiply yi with sigma I because it's again either it becomes +1 or it becomes -1, because that's yi's. Those are the labels. So I can absorb yi and minus into this expectation, resulting in another Rademacher variable sigma I prime, you may call it, and it's just half of expectation of S sigma supremum of this entire, like basically it's the Rademacher complexity of this class H within half. So the Rademacher complexity of loss function is 1/2 of the Rademacher complexity of this hypothesis set. And it makes sense. The intuitive way to think of is that truth table of 2 is condensed into truth table of 4 is condensed into two values. So you have reduced the complexity by 2 by half. Yeah. So now, composing all of these together, what you have is that the Rademacher complexity of the loss function is half the Rademacher complexity of our hypotheses. Now, if I set my G to be, in all of this analysis, if I set my G to be that loss function, what I have is that this will become the risk, because it's the expectation of the loss, so it becomes the risk. Risk is less than empirical risk plus the Rademacher complexity of the hypothesis set, because twice the Rademacher complexity of the loss function G, loss function class G, is the hypothesis Rademacher complexity of the hypothesis set. So that's what's written here. The risk is less than the empirical risk plus the empirical Rademacher complexity of our hypothesis set plus 3 times the log 1 over delta term, or the risk is less than the empirical risk plus the Rademacher complexity of the hypothesis. So now this makes sense, because now we have the Rademacher complexity of our hypothesis sets, and we can conclude, we can make comments on the loss, the risk of this particular hypothesis set. So remark says that this bound is distribution dependent, this one, and the second one is data dependent, sorry, because you need the sample S, you need the empirical Rademacher complexity. The first one is distribution dependent because this is the expectation of this. The real Rademacher complexity is the expectation of the empirical Rademacher complexity. So fine. But how do we compute the empirical Rademacher complexity? Again, in computing the empirical Rademacher complexity is computationally hard. So we don't really do it, but it's still nice to study. So is there any other combinatorial measures which are easier to compute? We'll see. We'll find out in the next part. So again, what I want to remember from this lecture, the proof is nice. It's nice to look over once and completely digest it on your own. But the main real key is how one defines complexity. How one could have defined complexity. I mean, think about it. If you were Rademacher sitting in your class and thinking, how can I define the complexity of infinite hypotheses? This is a very intuitive way to think about it. Like, what is the best possible correlation I can get with random noise? I throw random noise at this function class and see what is the best correlation I can obtain. And I keep doing it with different values of random noise and see if at all possible random noises I am able to get great correlation. That means my function class has really high expressive power. That means no matter what I throw at it, it has that power to fit any kind of random noise. On the other hand, if at all times I get a low number, that means no matter what random noise I throw at it, it has low expressive power. This is a straight up quantification of this notion of how good of an expressive power does my class have. And it is really nice. It is a really nice way of thinking about these things. But we will get to another even nicer ways to think about it. This lecture is amazing. This lecture is just amazing.